Imagine a universe where every force, gravity, electromagnetism, the nuclear powers, dances to a single cosmic rhythm. For decades, physicists have chased this dream. A unified theory that ties all of nature's rules into one elegant equation. Electromagnetism, the strong force and the weak force, they've been tamed by quantum mechanics, playing nicely in the subatomic sandbox. But gravity, it's the rebellious outsider, refusing to fit into the quantum mold. Its defiance has left us puzzled about black holes, the Big Bang, and the very fabric of reality. Now, a groundbreaking theory from Mikko Partinen and Jukka Toki at Aalto University might just crack the code. Published in Reports on Progress in Physics, their idea is a dazzling leap toward uniting gravity with the quantum world. Buckle up. This video will take you on a wild ride through the cosmos, exploring why gravity's been such a headache, how this new theory rewrites the rules, and why it could unlock secrets from the dawn of time. Let's dive in. Picture this. Two universes running on completely different operating systems. On one side, Einstein's general relativity, a 1915 masterpiece that paints gravity as the smooth curvature of spacetime. This is why apples fall, planets orbit, and black holes warp reality itself. This geometric marvel predicts everything from GPS satellites to the bending of starlight. Fun fact, Einstein's equations were so ahead of their time that they predicted black holes decades before we spotted one. On the other side, we have quantum mechanics, the bizarre rulebook of the subatomic realm. Here, particles pop in and out of existence, entangled across vast distances, and behave like waves and particles. It's the tech behind lasers, transistors, and MRI machines, and it unifies three forces in the standard model. But when we try to merge these two, it's like mixing oil and water. The math implodes, spitting out infinities, numbers so wild they make no physical sense. Why? Because gravity doesn't play by quantum rules, especially in extreme places like the heart of a black hole or the Big Bang's first heartbeat. The problem's been a thorn in physics side for over a century. In the 1930s, pioneers like Heisenberg and Pauli tried to quantize gravity only to hit a wall. By the 1970s, physicists developed renormalization to tame infinities in quantum field theory, making electromagnetism and nuclear forces calculable. But gravity? It laughed in their faces. Those infinities refused to be tamed, leaving us with a standard model that explains 99% of the universe, except gravity. This gap isn't just academic. Without a quantum gravity theory, we can't fully decode the Big Bang's first moments, when gravity and quantum effects ruled together, or what happens inside a black hole, where spacetime supposedly collapses into a singularity, a point of infinite density where physics just stops. Enter Partinen and Toki's radical idea. Instead of cramming gravity into the quantum box, they've built a new playground, an 8-dimensional gauge theory. Gauge theories are the backbone of the standard model, describing how forces like electromagnetism work through symmetries. Their twist? They use an 8-dimensional space populated by spinors, mathematical objects that generalize the spin of particles like electrons. These spinors dance in a higher dimensional arena, creating a symmetry that mirrors the standard model structure. It's like giving gravity a quantum makeover without breaking the rules of physics. To bring this abstract math back to our 3D space and 1D time, they invented the spacetime dimension field, a cosmic translator that ensures their theory matches reality. Here's the kicker. Their framework solves the infinity problem. Using renormalization, they've tamed gravity's wild infinities at the first order, and they're testing if it holds up deeper. This could mean gravity finally behaves like the other forces, calculable and predictable, no more cosmic tantrums. Why does this matter? Let's zoom out. Black holes are cosmic enigmas. Einstein's theory says their centers are singularities, but quantum mechanics hates infinities. This clash fuels the information paradox. Does information vanish inside a black hole, violating quantum laws? Partinen and Toki's theory could model black holes without singularities, preserving information and solving a 50-year puzzle. Then there's the Big Bang. The universe began in a flash 13.8 billion years ago, when quantum and gravitational forces were inseparable. Without a unified theory, we're blind to that moment. This new framework might let us simulate the Big Bang's first nanosecond, revealing secrets about cosmic inflation, the exponential expansion that shaped our universe, or even the birth of time itself. Mind-blowing fact. Some physicists think quantum gravity could hint at a pre-Big Bang universe, a cyclic cosmos reborn endlessly. How does this stack up against other theories? Take loop quantum gravity, LQG, which imagines spacetime as tiny quantum loops, like a cosmic Lego set. LQG avoids singularities but struggles to connect with the standard model's particles and forces. String theory, another contender, posits tiny vibrating strings in 10 or 11 dimensions, but it's complex and lacks direct evidence. The Aalto approach is different. It builds on the standard model's foundation, using familiar gauge symmetries to unify all four forces without exotic particles or rewritten spacetime. Plus, it's testable. Future experiments, like those at the Large Hadron Collider or with gravitational wave detectors like LIGO, might spot subtle particle behaviors or cosmic signals predicted by the theory. Imagine detecting a quantum gravity fingerprint in the universe's backgrounds. But there's more. The universe has a quirky imbalance. Way more matter than antimatter. Why? The standard model can't fully explain it. This new theory's symmetry-breaking mechanisms might reveal why matter won out, shaping galaxies, stars, and us. It could even shed light on dark energy, the mysterious force driving the universe's accelerating expansion, which makes up 68% of the cosmos. While the theory's still young, needing rigorous testing for higher-order renormalization and observational proof, it's a bold step toward a theory of everything. Partinan and Toki have thrown open the doors, inviting physicists to explore this cosmic puzzle. This isn't just math. It's a quest to understand reality's deepest truths. Will this theory finally unite gravity with the quantum world? Could it rewrite our cosmic origin story? Stay tuned as science pushes the boundaries of the possible. If you love this journey into the heart of physics, smash that like button, share with your curious friends, and subscribe for more mind-bending science. Drop a comment. What's the biggest cosmic mystery you want solved? See you in the next video.